Today is Actuarial Science Day, or maybe just Actuary Day for short here in Probability and Statistics. We're going to do some actuarial science modeling. There's some handouts on Moodle. There's a handout 1 that I made available. I'll make a handout 2 available as well. I want to tell you at the start here that the notation that I'm going to use will be sometimes consistent with the handout and sometimes not. And it's going to be confusing because it kind of conflicts with standard probability and statistics notation sometimes. So you got to be okay with that. I think it's good to imagine we could imagine we're in the life insurance business and we're talking about modeling people's lifetimes, but then we have to talk about people dying, which is fine, but maybe it might be nicer to talk about, well, appliances, okay? You are working for an appliance manufacturer like refrigerators, and people buy your refrigerators, and of course, refrigerators sometimes die. And we're trying to model how long the refrigerators are going to keep working before they die, ignoring problems that can be repaired. And, well, what do you do? And why might you want to model such a thing? Well, like for warranties, when you buy appliances, sometimes they come with a warranty. And, probably the value of the warranty is structured into the price of the appliance anyway, but maybe you have to pay extra for the warranty. And what do you get out of a warranty? You get maybe free repairs, or maybe it's free repairs, but you have to actually pay for somebody to come to your house to repair it, those kinds of things. Or maybe if your refrigerator completely dies, you get some new refrigerator at a discounted price. We're trying to model how long that refrigerator is going to last. What do? Probability models. And you're not sure what to try, so you just got to try different things and see how it matches the data. It's comparing the probability model with the statistical data. So you might try starting with, say a uniform model. Uniform model of refrigerator lifetimes. Okay, so that begs a question, how long do refrigerators usually last? You'd have to have some good information about that. Maybe you've gathered information about refrigerator lifetimes for your model refrigerator that's been on the market for a long time. Of course, maybe it's been updated, so this might not be valid anymore. And maybe the lifetime is 10 years. Now, hopefully you get refrigerators that last longer than 10 years. But just to keep things simple, let's say the mean lifetime is known to be 10 years, just to make it a nice round model to keep it simple. If we happen to know it's a mean lifetime of 10 years, an average lifetime of 10 years, and if we're using a uniform model, that means we should use a PDF that's a horizontal line, right? Uniform model. And if the mean is going to be 10, this better go from 0 to 20, because the mean is going to be halfway along the place where the PDF is positive. So your PDF in this case, I'm going to call the random variable in this case capital T, because it is an amount of time. We've almost always called our random variables capital X. But to emphasize this is a lifetime, how long the refrigerator is going to last, I'm going to call it capital T. So this is the lifetime of a random refrigerator. And the PDF then I could call little f of little t. But let me purposely also put a subscript here of 0. To emphasize that when you buy the refrigerator, it's 0 years old. It's like a newborn baby, right? That spanking new refrigerator is like a newborn baby. Of course, it doesn't grow, but and doesn't cry. But it's like a newborn baby. And yeah, if you were modeling people's lifetimes, the 0 here would represent a newborn baby that is 0 years old. I don't do this in the handout, but I'm doing it now. It is somewhat consistent with what actuaries do. So it's uniform. over the interval from 0 to 20. I'm assuming this is uniform over the interval from 0 to 20 to make the mean 10 if I'm using a uniform model. And since the area under the rectangle's got to be 1, as we saw last time, that means the height of this has got to be 1/20th. As a decimal, that would be what, 0.05. So the PDF is going to have a value of 1/20th if little t is between 0 and 20. And again, it doesn't matter, as always with continuous variables, whether I use less thans or less than or equal tos. Oh, for the sake of doing something different, maybe I'll use less than or equal tos. And it's 0 otherwise. Obviously, the mean is 10. The mean, mu, is 10 years. The variance of a uniform, do you remember it offhand without looking? Wasn't it b minus a quantity squared over 12? Isn't that what we found last time? So that would be 20 minus 0, 20 squared, 400 over 12. 400 over 12 is 33.3 repeating. Does the variance have units? Yeah, technically it would be, in this case, years squared. That doesn't make much sense, though. That's why we like the standard deviation better. And if I simplify this a bit, looks like the standard deviation is 10 over square root of 3. That should be the same as the square root of 33.3 repeating. If you want to double check it, 10 over the square root of 3. Yeah, about 5.77 years for the standard deviation, and the units there would be actual years. Okay, so these are the kinds of things that we'd be interested in. And as always, we could also use the PDF to find probabilities. What is the probability that the refrigerator is going to last, between 10 and 15 years, for example? Well, you'd find the area under the graph from 10 to 15. Just do it as a base times height. 5 times 0.05 would be 0.25, 1/4 probability of lasting between 10 and 15 years. If we're going to relate this to insurance, we also want to relate it to money, right? Because an insurance company is they have to think about money. And you also, when you do that, you have to think about the time value of money. You have to think about interest rates, and we're going to do that, but not yet. What I want to do now instead is talk about some other functions, including the CDF, but also some new functions that are important in this context for modeling. Of course, there is the CDF, which is capital F. I'll use a sub-zero. Again, in the handout, I don't always do that. This is going to be the CDF. As always, it's the probability of being less than or equal to the given number little t, the random variable being less than or equal to the given number t. In general, then, in a continuous context, it's the integral from minus infinity to t of the PDF. But because this random variable is a lifetime random variable, a survival random variable, it can't be negative, right? The PDF is going to be 0 when t is negative. And that's going to happen for all survival random variables, not just with this uniform model. So as a default, in this application, I'm always going to use a lower limit of 0. Yes, you could write minus infinity, but let's keep it simpler. Let's make it a 0. Make the upper limit the t, and here we put the PDF, and I think I'll go ahead and use my favorite Greek letter, xi, here for fun. Little f of xi to xi. Okay, it doesn't matter what letter you use there. Just don't use a t. Don't use a d. Don't use an f. Use something else. U, tau, whatever you want. I like xi. It's so much fun to make. And in the case where little t is between 0 and 20, I can write this. If little t is between 0 and 20, and get 1/20th t in the end, not 1/20th xi. because remember, you got to plug in the limits of integration. And ultimately, this means the CDF is defined for all values of t to be, well, 0 if little t is less than 0, t over 20 if little t is between 0 and 20, and 1 if little t is greater than or equal to 20. And so it's going to have a graph that looks like this. It's 0 over here, then it's a linear function with a slope of 1/20th there, and then it equals 1 past that point. And once you got the CDF, because essentially you did an integral to find it, you can use the CDF and subtract values to find probabilities. All right, here's a new function that we've never talked about in this class before. The complementary CDF function, 1 minus the CDF. In this context of survival random variables, it's called the survival function. And in the handout, it's labeled with the letter sigma. That's maybe not the best letter to use. Why did I use it in the handout? Well, I made the handout like 20 years ago when I was first learning this material. And I was learning it from somebody at the University of Minnesota, and he made his own notes for the class, and that's the letter he used. But to tell you the truth, most actuaries don't use a sigma. It's going to be the survival function. Most actuaries use an S for survival function to some degree, but there's yet another notation here that is actually more common. And to again emphasize, we got a newborn refrigerator. We put a subscript of 0 here. Actually, most actuaries use the following really weird notation. Pre-subscript T, P, post-subscript, well, 0 in this case. Pre-subscript T, P, post-subscript 0. You can just say TP0 for short. But the T is a pre-subscript and the 0 is a post-subscript. These zeros, by the way, very soon will become X's. What? X? Where would an X come from? The X will be a new letter representing how old the baby is, or how old the person is, or how old the refrigerator is at the given moment in time. Maybe it's no longer a newborn. Now, like with life insurance, that's important because you don't sell life insurance to newborn babies, right? They can't. You got to sell life insurance to people who can buy it. So it's important to think about people who are adults, say, and they are not babies anymore. And yeah, get what I'm trying to hint at there? But to keep things simple, we're talking about newborn babies or newborn refrigerators right now. And so we have these zeros here. This is my notes. This is a bit more standard for a survival function. Notice the word survival starts with an S. That's why this is an S. Oh, the Greek letter sigma starts with an S when you write it in English. Oh, there's reasons for these things. But it is confusing because, what, shouldn't sigma be a standard deviation? No, it's not. And actually, in chapter 6, we're going to learn about standard deviations called S. But still, no, it's not a standard deviation. Sigma's been standard deviations for random variables. S is going to be a standard deviation symbol for statistics. Standard deviation of data. But it doesn't mean that here. This is the most standard. I should really update my notes, but I haven't. Okay, my handouts. What is this? What does this represent? It's a positive kind of thing. It's a survival function. It is the probability of capital T being greater than little t, of surviving to at least little t years old. Instead of dying by little t years, you have survived to at least little t years, whether you are a person or a refrigerator. And this is the complement of the CDF. It is 1 minus the CDF. And for this example, that means it's going to equal, compared to this piecewise function, 1 minus 0 is 1 if t is less than 0. It's 1 minus t over 20 if t is between 0 and 20. And it is 0, 1 minus 1, if t is bigger than 20. And what will the graph of that look like? It'll look like this. And the values of this function give the probabilities of surviving to at least a certain age. Like if I want the probability of surviving to age 5, for example, I'd plug in 5 there. I do 1 minus 5 over 20. 1 minus 1/4 is 3/4. This would be a 0.75. I've got a 75% chance of the refrigerator lasting at least 5 years, 5 years or more. And yeah, again, because it's a continuous random variable, I could put a greater than or equal to there instead of a strict greater than. But because I want to relate it to the CDF in the most clean way, I'm putting a strict greater than there because there's a less than or equal to there. But it really doesn't matter because the variable is continuous. Okay, so this is a new kind of function that can be used to compute probabilities as well. Do notice then that, for example, if you're computing the probability that t is between A and B, and maybe I should call t really t sub 0. Oh, okay, that's too many subscripts. I could call a capital T t sub 0 to be consistent with all this notation, but I won't bother. Yeah, that's the integral of the PDF from A to B. Yes, that's capital F of B minus capital F of A. But it's also, let me use the most standard notation, it's also pre-subscript A P0 minus pre-subscript B P0. Notice the A and the B have switched the order compared to capital F. That's correct. I didn't make a mistake there. If I use the S notation, it would be S of A minus S of B. Wild and crazy notation doesn't go away. It keeps getting worse. Sorry. The ideas are things you can understand, though. It's the notation that's the thing that's difficult to wrestle with. Although there are new ideas, including another new idea here. Something called a force of mortality. Oh, negative word, mortality. Force of mortality. Mortality. Oh, the notation. It's called mu. Why mu? Because mu starts with M when written in English. Mu. Mu. Mortality starts with M. But wait a minute. Isn't mu always a mean? No, this is not a mean. Sorry. Maybe mu sub 0 of t. What is this defined to be? Intuitively, it's supposed to be constructed to be a measure of the likelihood. Say you buy a refrigerator. It's a newborn baby refrigerator. Say it's lasted 5 years. Or say you know it's lasted 5 years. Well, okay, it's really more looking ahead into the future. Pretend you know it's going to last 5 years. What's the likelihood that it will die within the next year? If you assume it lasts 5 years. Kind of a weird thing to think about. It's kind of a conditional probability. The force of mortality is proportional to that probability. It doesn't equal it, but it is proportional to it for small changes in time, like 1 year or less past a certain age that you assume it makes it to. That's kind of complicated sounding. It turns out to be best to define it to be the negative relative rate of change of the survival function. In my notes, I write that as negative sigma prime of t over sigma of t. If we were using S notation, we write it as negative S prime of t over S of t. If we were using the TP notation, we'd write it as, well, how do I write derivatives with the TP notation? I'm actually going to, okay, I'll write it as an ordinary derivative. ddt TP0 over TP0. So it's a negative relative rate of change of the survival function. The derivative of the survival function is its rate of change. If you divide the derivative by the function itself, it's the relative rate of change. Dividing the rate of change by the function value itself is relative rate of change. It can be interpreted as a percent rate of change. Typically, it's going to have a small value like maybe 0.04, meaning 4%. Although it's going to be negative here because the survival function in general is decreasing. Sometimes it's 0 in slope and value. The negative sign here actually makes this a positive quantity because of the fact that the survival function is decreasing. So this is actually a positive quantity or a non-negative quantity. It's not negative, even though there's a negative sign there. A non-negative function. What does it equal for our example? I guess I have to differentiate that. Right? That's our TP0 function, our sigma and S of t function. I guess I have to differentiate this, divide it by itself. As long as I'm not dividing by 0, I guess the force of mortality is going to be undefined when t is bigger than 20, because I'd be dividing by 0 otherwise. You know, it's funny, we're thinking about these graphs when t is negative, even though that doesn't apply to this real life situation. I did graph it when t is negative in these contexts just to emphasize the relationships with general PDFs and CDFs, but you really can just think about positive values of t and all this. Got to differentiate this and divide it by itself and put a negative sign in front of it. So in our example, okay, let's just consider the case where t is between 0 and 20. Negative, the derivative is negative 1 over 20. And the function is 1 minus t over 20. This is again if t is between 0 and 20. Now, technically speaking, if you want to be extra picky about it, you really should have strict inequalities here. Because that survival function, technically speaking, for this example at least, is not differentiable at 0 and 20. It's corners in the graph. That's not a super big deal for the 0. It is a big deal for the 20, because when t is 20 here, I'd be dividing by 0. The two negative signs cancel. And then this can be simplified a little bit by multiplying the top and the bottom both by 20 to get this. That's the force of mortality as a function of t. And what does its graph look like? When t is 0, it's 1/20th. But as t approaches 20, oh, there's a vertical asymptote, isn't there? The force of mortality goes to infinity as t approaches 20. What does that mean? That means, according to our model, 20 is the drop dead time for the refrigerator. It can't make it past age 20. Well, we already knew that from the uniform model here. No refrigerators make it past 20 years in this model. Now, of course, in real life they could, but in this model, they don't. 20 is the drop dead date. It's pre-programmed to die before it reaches 20. Remember, I said this is proportional to the probability, really a conditional probability of surviving a little bit longer if you know it survived so long. Like if you know a refrigerator has survived to 19.9 years, if you assume this baby refrigerator, it makes it that long, the probability of dying in the next few days is relatively high because this force of mortality is going so high. Why introduce this new function? Because it turns out to be convenient in many situations, especially for modeling. You might wonder, though, well, so if that's true, if this force of mortality is convenient for modeling, does that mean in doing our modeling, we should start with the force of mortality and work backwards to figure out the PDF and CDF and survival function? Sometimes yes. How? Go back to the definition of this force of mortality. Let me rewrite it down here. Oh, okay. I'll use the sigma notation like I did in the handout. But again, that's not very standard notation. So if I know mu, can I figure out sigma? Yeah, because effectively this is a differential equation in the unknown function sigma. You can solve this differential equation. And the most convenient way to solve it involves a little trick. And the trick is to realize that when you've got a function that's the ratio of a derivative to the original function, that's the same as the derivative of the natural log of the original function. Why? Well, just imagine doing that derivative. The derivative of natural log of x is 1 over x. So if I differentiated this, I get 1 over sigma of t, the subscript to 0. And then the chain rule would say also multiply times the derivative of the inside function, sigma prime of t. 1 over sigma of t times sigma prime of t is the same as that. You can write it as one fraction. Got a negative sign there still. Okay, multiply both sides by -1. The derivative of the logarithm of the function we want to solve for is negative mu0 of t, negative of the force of mortality. I guess I'm trying to solve for sigma t. I guess I should integrate both sides. Should I do this? Yeah, that is a good idea. Now in the handout, I write this initially as an improper integral, or excuse me, an indefinite integral. No limits of integration. And I just say you have to choose the limits of integration so that sigma of 0 is 1. Like that, right there. But I'll just jump to the kicker. You integrate from 0 to t. And I should use a different letter in here. I think in the handout I use a tau. Tau d tau. And now we're almost done. I got to get rid of the logarithm. Exponentiate both sides. Sigma sub 0 of t, or s sub 0 of t, or most standard tp0 is e to the negative integral of 0 to the integral from 0 to t of the force of mortality. And if you've taken differential equations, you might be looking at that and saying, that kind of feels like an integrating factor. Yeah, I think it is related to integrating factors. Yes, it is for differential equations. That's how you figure out, if you know the force of mortality, that's how you can figure out the survival function. What else do we want to know in these contexts? Again, we want to know the mean and the variance and the standard deviation. We already know the answers here for this particular model. Let's review the formulas for those because we're going to write new formulas for them. Well, the one for the second moment, I'm forgetting the way it goes. I'm going to have to look it up. The mean, which I'll use the word mean for mean instead of a mu. because there'd be two mu's. I think in the handout I do use a mu sometimes, but it's a different mu. It's not the force of mortality. The mean is the expected value of t is, as always, the integral of the variable times the PDF. So in this context, it would be this integral. In general, you'd have to go to infinity, though in this case, it would be good enough to do the integral from 0 to 20. And that, let's go ahead and do the integral from 0 to 20. Let's confirm the mean is 10, like we already know. Do this integral, we'll get what? 1/40th t squared going from 0 to 20. And yes, 20 squared is 400. The mean is 10 years, like we already knew. But there's a new formula for the mean in this context that says you actually don't have to integrate t times the PDF. Instead, you can integrate just the survival function, sigma of t or s of t, or I'll use the standard notation TP0. That takes proof. That's not obvious. I'm not going to prove it. You can effectively prove it with integration by parts if you make some assumptions about certain limits existing and being zero, actually. Effectively, your PDF has to go to zero fast enough to make it work. But this has got a name. I have no idea the origin of this name. I should look it up. I think maybe nobody in the world knows the origin of this name, but it's stuck. But I love the fact that it's stuck. It's called the Darth Vader rule. Why? I have no idea. Darth Vader rule. You can look it up. What's the Darth Vader rule in actuarial science? It's this, that you can, at least for a survival random variable, this doesn't work in general like with normal random variables, but for a survival random variable with certain assumptions on the behavior of the PDF, instead of doing the mean that way, you can do it this way. And that might be easier to do in some cases. So maybe it's a useful thing. In this case, let's confirm it gives us the same answer. What was our survival function over the interval from 0 to 20? It was 1 minus t over 20. It's not really any easier in this example. You could even say it's harder. But let's see that it hopefully still gives us 10. Do that integral, t minus t squared over 40, evaluated from 0 to 20. Oh, hopefully this works. 20 minus 400 over 40, and then minus 0. Yeah, that's going to be 20 minus 10. Yep, we got the right answer, 10 years. Darth Vader rule can be used to find the mean. What about the second moment? Second moment. E of t squared, by definition, it's going to end up being this. And here's where I'm forgetting how the Darth Vader rule works here. I think there's an extra factor of 2, but I'm going to need to look it up. Well, okay, in general, it'd be from 0 to infinity. I believe it's 2t f of t here. Or no, I think it's a survival function, sorry. TPX, TP0. I'm feeling, I haven't done that in a long while, so I'm feeling unconfident about it. Looking the handout. Yeah, there it is right there. I'm using the sigma notation there in the handout. Okay. But again, TP0 is the same as sigma sub 0 of t or S sub 0 of t. I don't use the 0 subscripts in the handout either, but I'm purposely doing it now. Okay, it can be verified by integration by parts and making certain assumptions. As always, the variance is computed by the computational formula and the standard deviation. Oh, there's another sigma. Okay, standard deviation is the square root of the variance. So we're modeling a bunch of stuff now. Still under the uniform distribution. You might wonder whether the uniform distribution is the best one to use. In the handouts, there's lots about exponential models, where you really do have to integrate from 0 to infinity instead of, say, 0 to 20 or something. Make sure you're reading the handout examples. Exponential models are talked about. The force of mortality for exponential models is constant, not this kind of function. That's a big difference. Which one's more accurate? It probably depends on the situation. Neither of these is accurate for lifetimes of people. Maybe the uniform is more accurate for appliances. You know, sometimes appliances break when they're really young. Maybe. I don't think the exponential model is accurate for either of these, though some people argue the exponential model is accurate for light bulbs. How long light bulbs last, though I'm unsure about that. The first light bulb that was ever made, or one of the first ones, is still shining. Thomas Edison made it or something. They got it in a museum. It's been shining for 150 years or something. It hasn't gone out yet. They really made light bulbs better back then. I think it uses a lot of energy and wastes a lot of energy or something, but it's just like really, really long lasting. Hasn't gone out yet, as far as I know. Something else that we need to talk about here. A few other things besides the time value of money. There's something called the Curtate random variable, which essentially rounds a person's age down, or an appliance's age down, to the greatest integer in that quantity, and it's a discrete random variable that's of interest, like in life insurance. But we also, probably more importantly, need to talk about conditional probabilities in this context. This is probably more important. And the notation here is somewhat inconsistent as well. So we've got our lifetime random variable T for a newborn baby, newborn refrigerator. Maybe I should use T sub 0. I'm given an attained age X. In my modeling, I'm interested in, with newborn babies, newborn refrigerators, I wonder what would happen, what kind of probabilities I would get if I assume the baby or the refrigerator makes it to age X. And what's the remaining lifetime? Like if I assume this newborn baby makes it to be a senior citizen, 65 years old, I wonder what the probability that they're going to live at least another 20 years after that will be. That's really a conditional probability. Assume they make it to age 65, how much longer do they have to live? Talk about it with refrigerators as well. In the handout, I use this notation, T of X. It is going to be a random variable that depends on the attained age X. So it's like function notation. And I call X with parentheses around it the client. Like this is a person attained age X. Why did I do that? It's because my teacher 20 years ago did it. But I don't really find that description in more books that I've read recently. The books that I've read recently actually use a subscript here, T sub X. What is this defined to be? It's going to be the remaining lifetime. Remaining lifetime when assumed to attain age X. When the person or the refrigerator has been assumed to reach age X. It's T minus X. Doesn't that make sense? lifetime when they were a baby minus their assumed attained age. So if a person makes it to age 65, their remaining lifetime random variable is t minus 65. If the refrigerator makes it to age 15, this is t minus 15. You want to think of x as fixed when we think about this variable. But it could be anything. So we kind of treat it like a variable, even though in our minds we're imagining it to be fixed.
So it's sort of like a constant.
Let's say this is x is you imagine x as a variable, but then you are or it's a constant, but then you are interested in, well, what happens if that constant changes, which sounds oxymoronic, but we can be flexible. So we're wondering, for example, what is the PDF? F sub x of t. What is the CDF? Capital F sub x of t. What's the survival function? Sigma sub x of t, or if you prefer, S sub x of t, or most standard, TPX. Think of x as fixed. Think of t as the variable in all these. What does that equal? And how about the force of mortality? Mu sub x of t. Let's go ahead and think about the survival function first. This is the way people typically think about it. Let me go ahead and call it TPX. So, okay, x is fixed. What should this represent? This should represent a survival probability, the probability of making it at least t more years. Assuming that they've made it from a newborn baby to age x. The probability that t of x or t sub x, I use of x in the notes, but I'm using the subscript here, is bigger than little t, given that capital T is greater than or equal to x. It's that conditional probability. By the definition of t sub x as t minus x, that's the same as the conditional probability that replace t sub x with t minus x and then add x to both sides. That capital T is greater than little t plus little x, given that capital T is greater than or equal to little x. All I did there was just replace t sub x with t minus x, and then I added x to both sides of the inequality. As a conditional probability, I can rewrite this probability as a ratio of two ordinary unconditional probabilities. And I'll use set builder notation, even though I'm not using it in the best way. The probability of the event that capital T is greater than t plus x, and intersection, the event that capital T is greater than or equal to x, divided by the probability that capital T is greater than or equal to x, right? This is just the definition of conditional probability right there. I'm using set builder notation just to emphasize that events can be thought of as sets. I'm not really using the set builder notation in the best way. I mean, if you didn't put the curly braces in here, I wouldn't make it a big deal. I'm also trying to do that because I'm putting the intersection symbol in there, but you could also just put the word and in there if you preferred. It's sloppy notation, admittedly. However, this event is a subset of this event. The event that capital T is greater than t plus x is a subset of the event that capital T is greater than or equal to x, at least if t is positive. Right? Because if the baby makes it past t plus x years, they've definitely made it past x years. So this probability can be simplified to just the probability that capital T is greater than little t plus little x. And now I'm getting rid of the curly braces. And by continuity, I can also write the bottom thing with a strict greater than sign, since capital T is continuous. Continuous random variable. Right, the strict inequality versus the non-strict doesn't matter. And that is the ratio to survival functions. That is, if we use the standard notation, it's really, it's funny, T plus X pre-subscript P 0 divided by X pre-subscript 0. Or in non-standard notation, I'll do the one in the handout. It's sigma of X plus T over sigma of X, a little less confusing. And I could put zeros there. In the handout, again, those zeros are not there. Ugh. So what does this equal for our uniform model? I need the formula that I derived for TPX. I need that formula again. So let's focus on this part of it. 1 minus T over 20 when the input is between 0 and 20. So I guess this would be 1 minus X plus T over 20 divided by 1 minus X over 20. As long as those inputs are between 0 and 20. For our example, this is our uniform example. And this can be simplified by multiplying the top and the bottom by 20 to 20 minus X minus T over 20 minus X. Now remember, think of X as fixed and think of T as the variable. Oh, wait a minute, did I make a mistake? No, okay, no, this is right. This is right. Actually, the simpler way to write it would be ultimately this. That would be the simplest way to write it. And it emphasizes that it is, when over an appropriate domain, it is a function whose graph looks like this. Intercept at 1. What is the t-intercept here? It would be 20 minus X. In reality, X does have to be between 0 and 20, but this set of inequalities really means T is between 0 and 20 minus X. I mean, I could put a negative X on the other side as well. I'm subtracting X from everything. But the key thing is that T is between 0 and 20 minus X here. That's the domain for where this graph is valid. It's technically 0 here and it's 1 over there. But this is the graph of TPX in our example. Think of X as fixed, it's a fixed graph, but X could be different things. And so you get different graphs for different X's. They'd all be straight, they have this shape, they'd all be straight lines in between here and here, but the t-intercept would change. As X gets bigger, this point moves to the left, right? If X is 0, it's 20. If X is 10, it's 10. If X is 19, it's 1. If X is 19.9, it's 0.1. We can also compute the force of mortality in this context. Mu X of T It's really the negative of the derivative with respect to t, and I'm using partial derivative notation to emphasize there's kind of like two variables in here. Even though in reality, I'm thinking of x as fixed. The derivative of this with respect to t is going to be negative 1 over 20 minus x. Simplified by multiplying the top and the bottom by 20 minus x and also canceling the negative signs. And you get this function. And that has a graph that looks similar to what it looked like before, but now the vertical intercept is at 20 minus, or the vertical asymptote's at 20 minus x. All this can be done without thinking about money. But where this really becomes useful to insurance companies or to covering your losses on warranty claims is when you think about money. Only got 4 minutes left. Let's start introducing what's in handout number 2. There's stuff in handout number 1 I haven't talked about here, though. That Curtate random variable idea that I mentioned briefly, it's where you round down. It's a discrete random variable, but we don't have time. I think it's most worthwhile to talk a little bit about the time value of money in our remaining time here. Money has a time value. What does that mean? $1 today is worth more, you might say, than $1 in the future. Why? Lots of reasons. Inflation, right? You can buy more with $1 today, or say $100 than you can 10 years from now, right? Maybe 10 years from now, if inflation stays bad, $100 will only buy you a gumball. You can buy more than a gumball now. $100 in the future is worth less than $100 now. There are other reasons. You could take this $1 or $100 or $1,000 or $1 million and you can invest it instead of using it right now. And it's going to grow to a bigger amount in the future. There's also just the fact that we want our money right now. Right? Give me that buck. I need it right now. I can't wait a year. Okay. Lots of reasons that money has a time value. How do you model the time value of money? The simplest way is with exponential growth, as if it's compound interest, or just, growth according to certain interest rates. $1 today is equivalent to 1 times 1 plus I to the t power dollars t years from now. Well, t years in the future. We say this thing, 1 plus I to the t, is the future value of $1 now. Another way to say that is $1 now is the present value of 1 plus I to the t dollars t years in the future. What is I? It's not the imaginary unit. No imaginary numbers here. It's the so-called, interest rate. Because you can relate it to actual interest rates of investments. What is time measured in? Years? That's most typical. And if so, this would be an annual interest rate. But it doesn't have to be measured in years. It could be months, and this would be a monthly interest rate in that case. Could be days. This would be a daily interest rate. Time could be measured in decades, and this would be a decadal interest rate in such a situation. Of course, usually you measure it in years. Again, 1 plus I to the t is the future value in t years of $1 today. $1 is the present value of this amount in the future. These are equivalent amounts. We can think of this another way. We only got 1 minute here. Hang with me. Another common way to think of this is to define a new quantity called v to be 1 over 1 plus I. In other words, 1 plus I to the negative 1. That's called the present value discount factor. And the final thing I'll say today is that you can think of this equivalence in another way. You could think of it as $1 t years in the future as being equivalent to v to the t dollars today. These two statements about the equivalence of these amounts of money are themselves equivalent to each other. They mean the same thing. There's different ways of thinking about it. Where we're headed next Tuesday with this is modeling a future payment. The refrigerator dies in 15 years. You got to make that warranty payment. What's the present value of that now? Not just of one refrigerator that dies exactly 15 years from now, but all the refrigerators that you sell that die at different ages. Random ages of death. You need probability to model that. Okay?